All right, so today we're going to be talking about U-substitution, and for this I'm just going to do 4 examples, and hopefully you guys can see my thought process and why I choose expressions to set equal to U and go from there. So, okay, here we go. The first one that I'm going to choose is I'm going to go with the integral of x squared times the square root of x cubed plus 1 dx. Okay, so if I have that as the integral, and just by using the power rule or what I know so far about antiderivatives, I wouldn't be able to just do this right away. I need another tool, which is why we're going to use U-substitution. So the first thing that we always try to do is set U equal to the innermost expression. So in this case, x cubed plus 1 is inside the square root. So I call that the innermost function. And what I notice that's beneficial is the fact that its derivative is a multiple of what this guy is right there. So let me show you. If I set U equal to x cubed plus 1, then du is equal to 3x squared dx. Dividing both sides by 3x squared, I get that dx is equal to du divided by 3x squared. So now let me go over here, and I say this is equal to the integral of x squared times root u, right? So I'm just replacing the x cubed plus 1 with the u. Times, instead of dx, I want it to be with respect to u now. So I'm going to say, instead of dx, well, dx is just equal to du divided by 3x squared. And look at this. This x squared term there and the x squared term there, they cancel out. So by doing this, we want to eliminate the x variable that is in here, and we only want to have the u variables left. And so I've done that now. So now this becomes, that 3 in the denominator can be pulled out as a 1/3. So this is equal to 1/3 times the integral of root u, which is u to the 1/2, du. So now we antidifferentiate using the power rule. So this is 1/3 times. The antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2 or times 2/3. And then don't forget your plus c. And then we always have to bring back what u is equal to in terms of x. So this is then equal to, so that's 2/9 times, now u to the 3/2 is the same as u times root u, right? So this guy right there is just u root u. So I would call this, x cubed plus 1 times the square root of that, or let's just leave it as to the 3/2, that's fine, and then plus c. So I brought back what u was equal to, which was x cubed plus 1, for my final answer, okay? So that's the first example of using U-substitution, and again, you saw that I chose x cubed plus 1 for 2 reasons. Number 1, that was the innermost function, and its derivative was going to be a multiple of this, so what I saw is those were going to cancel out. Even though there's that 3, that's just a constant, they can be pulled out, but the x variables canceled out, and that's what I was going for. Okay, so that's the first example. Let's go over a few more, like 3 more. So the next one that we're going to talk about is another one that should be pretty obvious for what you set u equal to, because we have it as in the innermost function. So we have the integral of e to the cosine of x, or sorry, let's make it theta, cosine theta, times sine of theta d theta. Okay, so now ask yourself, what is the innermost function? Well, it's going to be that cosine of theta, because that's inside the exponential expression e to the something. So I'm going to set u equal to cosine theta. I also see that its derivative is a multiple of sine theta, right? Because when I do this, I have du equals Well, the derivative of cosine theta is negative sine theta, and then d theta. And solving for d theta, I get d theta is just equal to du divided by negative sine theta. So this integral ends up being the integral of e to the u times sine theta, right, times d theta. Well, d theta is just equal to du divided by negative sine theta. And again, we have that the sine theta right here will cancel out with that sine theta right there. And I'm just left with, there's that negative, don't forget about that negative. This is equal to the negative integral of e to the u du, which is just equal to negative e to the u plus c. And now we have to bring back what u is equal to, so everything is in terms of our original variable. In this case, that was theta. So this is just equal to negative e to the u, but u is equal to cosine theta, plus c. Okay? And that's another example of using U-substitution to evaluate an integral that before we wouldn't know how to do that other than just by kind of guessing and checking. We would not know how to do that just by using the power rule or what we already know from derivatives in terms of antiderivatives. So that's the second example. Now let's go to one that's maybe a little bit trickier for some because it's not going to necessarily be an innermost function. So one example might be, let's have it be the integral of x over 1 plus x squared dx. Okay, so if I have this, I don't have a function that is inside another function like the first two examples. So you might say, well, do I set u equal to x squared? Or do I set u equal to 1 plus x squared? Or is u equal to x? Well, u is never just equal to x because that would just be changing the variables, but it wouldn't make the problem any easier to anti-differentiate or integrate. So let's do u equals 1 plus x squared. Now you might be saying, well, why would you do that? Why wouldn't you just do, u equals x squared? Well, I want to do that so that when I differentiate, du is equal to 2x dx, and dx equals du divided by 2x. So this ends up being, so going back to blue, this ends up being the integral of x over u times dx, but that's just du over 2x. And again, we see that these x variables cancel out, and so I'm just left with, this is equal to 1/2 integral of 1 over u du, which is 1/2 times the natural log of absolute value of u plus c. Then I replace this u with what it's equal to have 1/2 ln of absolute value 1 plus x squared plus c. Now the one thing I'm going to say about this problem is I don't need these absolute value marks anymore because what's inside here is never negative, right? 1 plus x squared, that's always positive. So really, I don't need those, so I could just call it 1/2 ln of 1 plus x squared plus c. And if you really wanted to, you could call it ln of root 1 plus x squared by applying that 1/2 up as the exponent. But that's another example. And the last example that we're going to go over that is similar to this is I'm going to make it the integral of x over 1 plus x to the 4th dx. So for this one's a little bit weird because I don't want to just go with u equals 1 plus x to the 4th because then you could see that dx is going to be equal to 4x cubed du. So this seems a little bit weird, but just go with it for a little bit. If I set u equal to x squared, well, why would I do that? Well, first of all, I can see that its derivative is going to cancel with that guy, so that's nice, right? du equals 2x dx. And then this would be the integral of x over 1 plus, well, if u is x squared, then this would just be u squared. And then this would be dx, which is just times, over here, dx equals du over 2x. Du over 2x. And those x's cancel out. And so this ends up being 1/2 times the integral of 1 over 1 plus u squared du. But you might say, well, I don't really know what that is. But you should remember what that is, because that's just the inverse tangent. So this is 1/2 times arctan of u plus c, right? And now we say, what is u equal to? Well, u is equal to x squared. So this is just equal to 1/2 arctan of x squared plus c. So sometimes you have to mess around a little bit with it. These ones are not as intuitive as the others. The other ones are that are the easiest are the ones where the innermost function is what you set u equal to. All right, so I hope you guys find that helpful. Maybe I'll be putting a few more examples up later, especially of tricky U-sub, but for now that should get you going.